Okay, in order to meaningfully be able to talk about doing physics, we have to know what the heck it is we're measuring. And in order to do that, we have to have units so that we know what the heck we're talking about. As you recall from Physics 243, there are a bunch of base quantities. Classical mechanics only concerns itself with three of them, namely mass, length, and time. These quantities are operationally defined, which if you remember, that's basically a recipe for saying how to measure the quantity without actually saying what it is. And there's a very good reason for that. That's because we don't know what they are. We are only just barely catching on that space-time is a thing. And so trying to say what length is or time is, or for that matter what mass is still an open research question. But we can communicate effectively as long as we have some sort of consistent recipe for measuring things and comparing measurements. So for instance, we generally say that mass is that thing that a balance measures, although there are other definitions. That's the one in common use. Length is that thing that meter stick measures, and time is that thing that a clock measures. Now these physical quantities are themselves independent of the idea of units. For instance, with mass, we usually note the physical dimension itself by putting a nice little, putting an uppercase M in square brackets. Same for length. We'll do an L. And for time, we'll do a T. Now, units that we could use, those for case of mass, those include things that we would expect, like the kilogram, and maybe things you're not quite so comfortable with, like the slug, which is the traditional English unit of mass. Similarly, length can be measured in meters, can be measured in feet, it can be measured in arshins, which is an old traditional Russian unit. You get the idea. Time, we usually do seconds, but we could just as easily do hours, years, eons, whatever. As long as we have an agreed upon standard to compare, if I say that something is 5 meters long, everybody in the world knows what a meter is, and they can take their meter stick out and they can lay it out 5 times and have just as good of an idea as me. Just for quick reminder, the meter, the kilogram, and the second constitute what's called the Mks system. For meter, kilogram, second. And they are part of SI, which stands for Système International, which is French for the International System. Not that you really need to have this committed to memory or anything, but it's just fun. A meter is the distance that light travels, so say I take myself a laser or something like that. I shine it out. It's the distance that light will travel in a vacuum in 1 over 299,792,458 of a second. To get a second, what you do is you take yourself a nice atomic clock, you drive a certain hyperfine transition of the cesium-133 atom. And when you count 9,192,631,770 of those periods of oscillation, you can say that a second has elapsed. Compare this to the official definition of the kilogram, which is the mass of a blob of metal in France. Now, officially, it's kept at the International Bureau of Weights and Measures, which by treaty is technically international territory. And in fact, the treaty says that if anyone were to attack that territory, it would be considered an attack on all nations. Now, if you notice here, one of these things is not like the other. In fact, I'm going to draw a line right here. If we look above this line, these are what we call lab reproducible standards. And if we look below the line, this is what we call an artifact standard. Oops. So what's up with that? Lab reproducible standards are generally considered a good idea. Pretty much any fool with $1 million can go and build as good of a meter and as good of a second as anyone else in the world. Artifact standards definitely have a problem in that, since you're referring to a specific blob of metal in France in this case, if you drop the blob of metal or something like that, you can have a problem. In fact, every decade or so, the major national authorities take their copies of the International Kilogram. The United States National Institutes of Standards and Technology is custodian of copies 3 and 13. For some reason, we like copy 13 a little better, so that's the kilogram in the United States. But anyway, we'll fly our copies back to France once a decade and compare with the blob of metal that is stored in the vaults there. And normally everyone goes and compares and they see that all the blobs of metal are the same. Turned out the last time they did this, thing that everyone is quite clear on is that for some reason the mass of the blob of metal in France got heavier. All the copies are still reasonably consistent with each other, but definitely the blob of metal in France got heavier. Now it's made of a platinum iridium alloy, which is very resistant to corrosion. It's kept in a vacuum, not as hard of a vacuum as you would like, but it's kept in a vacuum to try to resist corrosion more. But it's just hard to say what happened. But maybe there's just some contaminant on there or whatever, but try as they might, came to a conclusion that that blob of metal has definitely gotten heavier. Now people are hard at work on other standards, other ways to redefine the kilogram standard. Hopefully some of those will have some success, and one of them will get adopted so we can get rid of the last of the artifacts. Believe it or not, we used to have an artifact for the meter. It's a rod of platinum iridium. A lot of the things that we had were artifacts, but the kilogram is the only artifact we have left, and we would dearly like to make that one go away. Alright, so from that thought, let's go ahead and pick up on thinking about what we can at least use physical dimensions for. Now remember, the dimensions are not the same thing as a unit. So we've got mass, we've got length, and we've got time, like so. Now you can express those dimensions in any units you like. And any physical quantity can be expressed Ty can be expressed as some combination of powers of the dimensions, where I'm just picking alpha, beta, and gamma here to be my powers. So for instance, if I wanted to figure out the dimension of work, that would be some dimension of mass times 2 dimensions of length over 2, over 2 powers of time dimensions. Now what's nice about this is that you can do what's called dimensional analysis, which is a good way of checking your work. In 243 we usually called this check your units, and a lot of people still do that. Just as you go on, though, it becomes a little handier to think in terms of dimension, just because sometimes we pick strange units that are like natural units, where you say things like the speed of light is equal to 1, and it's not 1 anything in particular, it's just the number 1. At that point, checking units gets really hard, but checking dimensions still works out. Okay, so let's take an example here. So let's say you did some sort of calculation, you got that the work done on something was equal to 2 MV. You want to know, was that correct? Well, we can check. We know that the dimensions of work are going to be mass times 2 powers of length over 2 powers of time. And we don't particularly worry about the number 2. It doesn't have any dimension. We'll have, doggone. We'll have a power of mass from the mass here, and then the dimension of velocity is length over time. And you can go and say cancel, 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 cancel. So we're left with 1 over there. And length over time equals no dimension, no. And so the answer is that is wrong for sure. That's the advantage of math class over physics class. Or sorry, the advantage of physics class over math class is that you can always, since the symbols always have meaning, you can always check the dimensions to see if you made a mistake, and I expect that you would do that. Now, just as another example here, let's say you got something like work equals mv squared, and you want to know if that's right. Well, you can go and look and say, all right, we know that work has units of mass, dimensions of mass, 2 powers of length over 2 powers of time. And we want to know if that is equal to, well, we got a dimension of mass there. This is going to be length over time, but I'm squaring it, so L squared over T squared. Hey, awesome, it checks. So this is right, right? Well, the best I can do is say maybe. If you think about it, this looks like it's 2 times the kinetic energy. So most likely you missed yourself a factor of 1/2 right there. Now, checking the dimensions will never catch that missing 1/2. So in other words, if the dimensions check, that's not a guarantee that you're right. But if the dimensions don't check, that is a guarantee that you're wrong. Okay. One of the other things that can be very helpful for us, if you're just trying to fish around and get some kind of idea of what an answer might sort of look like. There's a famous saying due to Dirac that a physicist should not attempt to undertake a calculation for which he does not already know the answer. And that's very sage advice, but how do you get some idea of at least roughly what the answer would look like, what I call the shape of the relationship? What you kind of want to do in a case like that, so we'll just say guessing shape of relationship. You're going to have to use your intuition here to intuit what might be appropriate variables. Doggone it. And then you can play around with powers to see what gives the right dimension. So see what powers give the right dimension. So let me just do a quick example of that. I always find that when you're working in mechanics, or heck, just about anything, starting first with the most intuitive example you can think of is usually the best. So one of the things you'll see me do a lot in this class is dropping a rock. So we're going to let rock drop some height y, and we'll be nice and assume it's in a vacuum. And we would like to know just before impact how fast is it going. And it'll be nice and assume that it was at rest to begin with. Alright, so I think we all know where this one's going, but let's just say we didn't. We can look at this and say, well, what could it depend on? Well, my intuition tells me certainly it's going to depend on the height. We know that the higher we drop things from, the faster they tend to go. And it's probably going to depend on the gravitational field strength. We certainly know that dropping things on the moon, things don't speed up as fast as they do on the Earth. So we're going to guess that depends on G and Y. Alright. So the game we can play is then we can say that my velocity is going to, I should say proportionate. Yeah. Let's try that again. My velocity is going to be proportional to g to some power alpha, y to some power beta. And then we just play with the dimensions and see what happens. Velocity we know is going to have dimensions of length to time. Now we can switch from proportionality to an equal sign when we're comparing dimensions, because any numerical factors don't have dimension, so we're assured inequality. G has dimensions of length over time squared, but we're going to raise this to the alpha, so this is length to the alpha times squared to the time to the 2 alpha. Similarly, y has dimensions of length, and then we're going to raise that to the beta. So now if we go and take a look at our powers over here, the powers here are both 1. So that means that alpha plus beta has to equal 1 for the numerators to work out. And for the denominators to work out, we get that 2 alpha has to equal 1. Well, that immediately gives us that alpha is equal to 1/2. And then sticking back in over here, that yields, whoops, there we go. That yields for us that beta equals 1/2 as well. So the shape of our function, we can say that v is likely proportional to root gy. So I call that right there the shape of the answer. Now, the actual answer turns out to be missing a 2 inside the root. But if you know roughly where you're going, that you're expecting a root 2gy, then at least as you're doing your calculations, if you see that you're heading away from there, then you know you're in trouble and you should probably revisit things.